Good morning and welcome, one and all, to another edition of Finzics. It's Mr. Finn coming at you from neighborly Northville. Hope everybody's having a great week out there. We're very near our end of the week time frame, so a couple things today, guys. Wrapping up with you, we had a couple of videos from different sources this week. You had the crash course video on magnetism. You had the Dr. Bruce DiNardo of the Postgraduate Naval School doing the fundamental law of magnetism, which is a deflective law. Now that shouldn't be any different than you seeing a charge come across your screen and go through a magnetic field. A moving charge entering a magnetic field would deflect. And why would that deflect? Well, the moving charge, remember from Monday's activity or lesson, that the moving charge has its own magnetic field, and that magnetic field will interact with the magnetic field that it's moving into. So we use the right-hand rule to describe that, and I'll go through that a little bit later. After that, we have the magnetic field lines as seen from a magnetic field line generator with the tiny compasses. So hopefully you guys are getting comfortable seeing magnetic fields. They're very similar to electric field lines, which we did see together quite a while ago. But today, have to answer a quick question. What is the biggest magnet in the world? And according to your earlier discussion, Mr. Finn, you mentioned that bar magnets, if they were magnetized, if they were jostled or jumbled or turned around or dropped and thrown around a little bit, they could actually demagnetize to a certain degree. Could the largest magnet in the world do that as well? Let's have a little think about that, and we'll come right back to that. Before I come back to that, though, remember that we are doing a Google form today at 3 o'clock. So, wrapping up the magnetism section here real quick with a Google form at about 3 o'clock. And then we'll be on to electromagnetic induction next week. Make sure you guys are keeping up with the homework. All right, let's take a look at that. Can the largest magnet in the world ever be demagnetized? And what is the largest magnet in the world? Did you have to think about that? Let's do a quick little work on our board to find out what's going on. Okay, guys, real quick. This is a drawing of the planet Earth. Earth is the largest magnet in the world itself. The world itself, the Earth is a magnet. It has its own magnetic field. Now, how does a hunk of iron moving through the universe have its own magnetic field? You may be asking yourself that. Well, scientists don't quite know. They believe that it's the result of moving iron magma in the Earth's core, moving molten magma that's creating this magnetic field. As a result, has a North Pole and a South Pole with magnetic lines going out and coming in. So the Earth's magnetic field actually uses itself as a defense system, deflecting debris and away from certain areas and allowing the Earth to defend itself against space crap. Anyway, this North and South Pole are great because we can use it for navigation purposes. We can just take a normal compass and line it up in the Earth's magnetic field and determine north and south. Seafaring people have been using this as a way of navigating for a long time. As a matter of fact, before GPS, this was our primary mode to know what way we were going. Cars used to be outfitted with compass actually around the dashboard. Anyway, what's surprising though is that this magnetic field is not exactly stable. I don't know if you guys got a chance to read section 36.9 where it says, whatever the cause, the magnetic field of the Earth is not stable. It has wandered through geologic time. Properties of rock strata, blah, 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 blah. Oh, from the Mid-Atlantic Trench. What is our Mid-Atlantic Ridge? The Mid-Atlantic Ridge is a place in the Atlantic Ocean where the continental plates are pulling apart and magma is coming up from the as the magma comes up from the ridge, it cools, and it cools very quickly in the magnetic field of the Earth. So the evidence of the floor area by the ridge is interesting because it looks like the magnetic values are different if you go away from the ridge. North, 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 north. So there's lines of rock strata that are magnetized in the magnetic field, north, north, north. And then some fuzziness, and then north the other way, and then some fuzziness, and then north the other way. Same thing with the south, which means that the North Pole has switched to the South Pole and vice versa through various parts of time. Interesting. Now, if you read on, 20 reversals have taken place in the past 5 million years. The most recent occurred 700,000 years ago. But other reversals occurred at 870,000 years ago and 950,000 years ago. Studies of deep sea sediment indicate that the field was virtually switched off for 10,000 to 20,000 years, just over 1 million years ago. This was the time that modern humans emerged. Switched off, which means we had no magnetic field. Imagine if you were using a compass to get around and the compass just started not working right. Well, it would take a little bit of time for that magnetic pole reversal to happen. It would take a little time for the magnetic north to become zero. But recent indications that we are in for a magnetic pole reversal within the next 100,000 years, or 2,000 years rather, are very prevalent. We've had 5% of a decrease in the Earth's magnetic field over the last 100 years. Now, what does this mean? Cats and dogs living together, total pandemonium? No, I think not. But we might be in for some big climate change as a result of North and South poles switching off and then flipping back on again the other direction. Who knows what can happen? Maybe there'll be an ice age. Anyway, guys, you might want to look that over. I'll try to find an accompanying video on magnetic pole reversal. But let's wrap up. Okay, guys, so with the Earth being the largest magnet in the world, obviously we don't know about the other planets. We may have some situations where we do have a magnetic field around lots of different celestial objects. But for now, why don't we say that the answer to our question today, what is the largest magnet? It's the Earth itself. And the Earth's magnetic field is not exactly stable. It does change every so often. Now, it's not very, very common for that to happen, as we saw from these these figures about when those occurred. But we are about due for one in the next couple thousand years. Anyway, guys, I hope it's okay. Get to your Google Meets and try the Google form today. If you have any questions, please email them in or get to those Google Meets and ask. We'll be dealing with electromagnetic induction starting next week, so it's a little bit more complicated. I told you I'd go through that charge example again. So let me go through that with you. Let's say that there is a positive proton coming across our screen like this. Coming across. So I'm going to say the positive proton's coming up. Let's say that there's a magnetic field coming at you. At you. So it's coming out from my chest and towards you. The magnetic field's going this way. So we're going to put a B field that way. Positive charge, a single proton coming this way. Now, how do we predict which way the proton would go? We use what's called the right-hand rule. If you take your fingers and you move them in the direction of the moving charge, so I'm going to move, if my charge is coming this way, I'm going to move my fingers, my right hand this way. Curl your fingers in the direction of the magnetic field out towards you. So I'm going to come this way and out towards you. Stick out your right thumb. That is the way that the particle would be forced or deflected. So this particle coming in here, magnetic field going out, it would deflect downward. That goes with the fundamental magnetic force law as shown by Dr. Bruce DiNardo in one of our earlier videos this week. Now, the right-hand rule applies to positive charges, protons, or ions that are positively charged. What if it's negatively charged? Well, you just reverse the direction of your right-hand rule. In other words, if it were an electron coming this way, curling toward the magnetic field, your right-hand rule would predict a deflection of down, but the electron deflects up. So it's exactly the opposite force on the particle. Now remember, that's the electron's path. The proton's path is down. The force of deflection is down. It's always 90 degrees away from the path of the particle and the magnetic field. So if your particle's coming this way, and your magnetic field's going that way, your force goes this way because there are 3 dimensions in which to work. So you've got velocity of the particle, the magnetic field, and the force of deflection. If you'll remember from Dr. Bruce DiNardo, that resulted in an equation called F equals QVB. Q being the charge, V being the velocity of the particle, and B being the magnetic field. F equals QVB. That is the force that the proton or the electron, the charged particle, would experience by moving into this magnetic field. Again, that comes from the magnetic force law, guys, and please view that video from Dr. Bruce DiNardo of the Naval Postgraduate School if you have not already done so. Okay, guys, have a great day, and remember the Google form today at 3 o'clock, and we'll see you next time.